Hi. Now we continue from the previous problem where we were making the grades, and here we compile some very simple statistics in a table on a given set of grades. So we are supposed to have three columns. The first column is just the grade, and that will go from A to D and then F. And then we have a column that says how many of each there were in the given list of grades. And finally, we want the percentage, but while we do want it as a number, we also want it rounded off to look nice. So up to a single decimal position. Here are some sample grades. Now it happens to be that all the grades are present and they're all in groups, but it doesn't matter, as we'll see based on the algorithm. Here's a little lambda, a defen. We can take the right argument here with omega, the rightmost letter of the Greek alphabet. We could also take a left argument, and if you were to do that, then I would, for generality, you use the alphabet of letter grades. Like this. However, there is a so here we have the left argument and the right argument next to each other. However, there's a trick. We can put in a special little statement. Diamond is the statement separator because diamonds are unbreakable. If we try to assign to alpha, which is the leftmost letter of the Greek alphabet, indicating the left argument, when there is already a left argument, then that whole statement is ignored. However, if we do not supply a left argument, that statement is executed. So I think that rather than using a regular variable to keep these letter grades, we should use alpha, because then if you want to override it with a new system that uses different letters, that will work too. Okay, now we are ready to get started. We've got our left argument, which are the letters of all the different grades that can appear. We have the right argument, which are the grades in question that we're going to compile statistics on. And the first thing we want to do is find out how many there are of each. Then we can use that to compute the percentages. And one way to do this is to do an outer product. Well, it's called product, but it's really not a multiplication here, but an outer equality. That means we take every element on the left, those are the letter grades, and compare to every element on the right, those are the grades coming in. And we get a comparison table. So here we can see that since we begin with a bunch of D's, and each row here represents one grade, A, B, C, D, we get a bunch of 1s here, and then we get a bunch of A's, they're up here, and so on. Of course, this means that we can do the count of each one simply by summing, and we write that as a plus slash. So here are the sums or counts, if you want. We can call that S. In order to compute a percentage, we want to know how many letter grades are there in total. We can use the tally mark to tally the number of elements in the right argument. Then we can take the sums and divide by that, giving us fractions. In order to get percentages, we want to multiply by 100. And then we want to round off to a single decimal. Here's a neat way to do it, but maybe not the best. We'll fix that later. We can use the format function, which converts numbers into characters. So this becomes one giant character vector with digits. You won't be able to see a difference because it has the same textual representation. However, we can give it a left argument, which is exactly the number of decimals. If you were using a negative left argument, it would be the number of significant digits. We can try that for a moment. So if we say we want 2 decimals, we can see that we get 9.68 but 25.81. If you do -2, then we get a scaled format so that we can indicate the precision exactly, and we say we get exactly 2. But for now, we just need a single decimal. This is not an array of numbers, this is an array of characters, so we want to convert it back again to numbers. And with that, we just need to construct our table. This is a vector, and we need to have a matrix, that is a table, a two-dimensional array. We can use the table function to create a table from a vector. So here we get a column vector or single column matrix, and with that we can concatenate it together with the sums or the counts of each one. And finally, we can concatenate on the far left the letters themselves, and this solves the problem. However, going via a character representation seems a bit iffy just for rounding, especially since the way we're going back again is actually execute or evaluate. So we're taking this whole character vector, which are all these rounded numbers, and executing them as APL code. That's generally a bad idea, both for performance but also for safety. If somebody were to somehow inject something in there that's dangerous, then our whole system could fall over. Let's do this the arithmetic way instead. We don't have a round to a specific precision function in APL. However, we do have a flooring function. We can write rounding in terms of flooring. We don't want to round to whole numbers. We want to round to tenth of numbers. So instead of multiplying by 100, let's multiply by 1,000. That gives us tenths of percent. Now we just need to do the rounding, but flooring is not going to give us the right result. This is floor. You can kind of see that's a wall and a piece of a floor. And that is because we need to round up when we have 7 and 8 here. In fact, from 5 and onwards, we want to round up. And this just rounds down. It's floor. If we lift up all the numbers by a half, then anything that ends with 0.5 or higher will be lifted into above the next higher number. And now we can see how 96.7 and 225.8 were rounded up, whereas everything else was rounded down. So this is the type of rounding that we want to do. But our numbers are too big now. We want to divide them by 10. Of course, this has 10 divided by, but the commute operator can swap the arguments to the division function, so that this is 10 into whatever we have over here, rather than the opposite. And this solves our problem in a safe and efficient manner. Thank you for watching.